Hello, everyone. Today I'm going to be talking to y'all about data science and machine learning, how you can use that, how it can help you, and why you should do it. All right. So a little bit about me. I'm class of 2022. Hey, whoop. I'm a senior, and I'm majoring in computer science and applied mathematics. Previously, I've worked at a company called Deep Haven Data Labs, which they make like software for hedge funds, and then SmugMug and Flickr. And right now I'm researching Alexa here at A&M. So if y'all want to say, if you have an Alexa at home, you say open Howdy y'all or open Howdy y'all beta to your Alexa, you'll hear our skill and learn how to make scrambled eggs. So yeah, that's just a little bit about me. Can I take a poll of y'all? Like, who is a freshman? Raise your hand. Okay. Who is a sophomore? Cool. Juniors? All right. Seniors? Cool. See, in data science, we call that a distribution. Okay. And then just George. And then also majors. So who here is a computer science major? And then CE? Other? Okay, cool. You can shout it out if you want. Yeah, this is a very Socratic seminar, so don't feel afraid to say whatever you want at any time. But yeah, the reason I asked that is I want to assess y'all's knowledge. Who here has heard of data science and machine learning? Cool. Who here has done stuff in data science, machine learning, I don't know, opened imported pandas? NumPy, something like that. Yeah, that qualifies. You're now a data scientist, and you can write that on your resume. Okay. I just want to gauge, where we are, so I know what to talk about. Cool. So, what is data science? Does anyone have any ideas? What do they think data science is? Like some kind of really rigorous definition, like something by the book.
I guess mostly just massive data collection and then building algorithms. Sort of patterns in that data.
Okay. Yes. Mass data collection and building algorithms to find patterns in data. Yep. That checks out. Anyone else? Cool. So how I define data science is when you try and answer questions, but with numbers. And there's a lot of different ways to think about it, and that's probably better, or definitely more rigorous. But it is a very broad field, where there's a lot of people I think can claim to be data scientists. The really important part of it is the science in the name, right? It is a science. There are techniques and defined approaches to going about things. But at the end of the day, it just boils down to informed decision-making with numbers using quantitative techniques. Yeah, cool. So another way to think about what data science is we're cleaning our digital rooms. So for any type of labor, right, any type of work, if you clean your room, you take something that's unstructured and you structure it. You make it into something that is useful to you. Now you know where your keys are, or where stuff is in your room. It's easier to use, etc. You build a house, you make a bunch of unstructured materials into a building, something that's useful. So we've come to the point in society where we're now doing that with data. There's just information that's unstructured and unusable, hard to navigate. It's just kind of sludge. So a data scientist will restructure that or process that into something that's useful and usable to people. So it's a big picture way to think about it. More specifically, it's fast question answering and testing hypotheses. So if you have data about something, could be anything. So let's say you have data about, I don't know, temperature and frogs' reproductive cycles or something like that. And you have a hypothesis that temperature affects, how often frogs reproduce, something like that. That is data science. You are trying to answer questions using the data that you have. And I mean, it could be anything. Any question that can be answered with numbers requires or could use a data scientist. So the other big cool thing about data science is that your hypothesis testing is fast. So I had a phase where I thought I was going to be a mechanical engineer, and I did some research. And they were like, we're going to extrude like this jelly out of this hole and then put it in a cup for like 7 hours and then record the temperature. It was too much. And I realized that, in the physical world, things are slow. And you're limited by how fast you can set up experiments and test hypotheses. It takes like hours and hours. The cool thing about data science is you run your model, retune your parameters, run it again. You can check and test hypotheses really quickly. So that's something that's neat, and it's also part of what defines a data scientist, that it is a science. Do y'all remember like those scientific method little things like in elementary school? It's like hypothesis, blah, 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 blah. You actually, yeah, that's true. That's crazy. Like they're right. You do that, but just really fast now. So data science. Cool. So, oh no, where did this go? Oh, nice. I forgot I did that. So as for how you do this, how do you test your hypotheses? There's Python and R. So those are like the two base programming languages that like a lot of data science is done in. And R is more scientific. Python is general purpose, also scientific now. And then there's data manipulation. You have pandas and NumPy and Py and dplyr and R. Then you have data visualization. There's matplotlib and Seaborn and ggplot. And then you have machine learning, which is like scikit-learn and PyTorch and Keras and TensorFlow and Taurus. And then Spark and Scala for distributed processing and Hadoop and Scyther. And then you have MySQL, MongoDB, Tableau, Alteryx, Articuno for like queries and stuff like that. And like if that sounds like a lot, it is, and it's a lot to learn, and you have to learn it all in order to be a good data scientist. But you don't worry. It's simpler than that. It's not that hard, but it's important to get started somewhere. If only there was like a place where you could get started with some of these technologies, try and test some of your skills and dip your toe into like Python or R, preferably here at Texas A&M University, where you can maybe meet companies. That would be crazy. Too bad there's not anything like it. Oh, wait, there is. It's TAMU Datathon 2021. Please come. Scan this. Ask me. If you have iOS 15, zoom in and click that link on your phone. Our event will be October 16th to 17th. It'll be tons of fun. We'll have a great time. Y'all will learn data science. So that's cool.
It looks really good, guys. I will say, like freshmen and sophomores here, that if you need something like a project to show up on your resume, and then we can do it in the like meeting at Datathon or at any hackathon. Highly recommend it.
Exactly. And going up, and by the way, I don't know if y'all noticed, but like some of these were Pokemon. And the point I'm trying to show is like, there are so many technologies and you're not going to know them all. And I know like 2 here, so don't worry about it. It's more important to just get started with something and get your feet wet, right? Like open a CSV file and then you're good. Like that's it, right? Like just do something. So yeah, apply for TAMU Datathon 2021. Okay. But for real, how would you get started, and how would I recommend you like start your process with data science learning? I am a big Python fan. I think R is great, but it's not as widespread as Python. There's so many resources for getting started with Python online. I'm a huge fan, if anyone has not used them, don't worry about it, but of Jupyter notebooks. They're basically these like notebook files that you can execute code in cells, and then also run a Markdown, which is kind of like a text language where you can format things nicely, even do LaTeX if y'all have done that for math classes. So I would recommend getting started with Jupyter Notebooks as well. For like your libraries, your bread and butter for data science will be Pandas and NumPy in Python, which are great for data manipulation. I think a great starter ML library is scikit-learn. It also inherits a lot of the syntax from Pandas and NumPy. And then you'll learn this when you're kind of gathering data sources, but I think SQL is really important to get some kind of grasp on. And this is a lot, but I would say this is also a ranked list. So learn Python, then maybe open a Jupyter notebook, then progress that way. Yeah, I started only turning in Jupyter notebooks to my professors, even my math professors. They like it. So, start. Okay. So, does anyone want to do data science here? Okay, we're getting some, an aggressively lukewarm response. But luckily, by the end of today, it'll be all of you. Right. So, you should want to become a data scientist. What do y'all want to be, like a software engineer? Raise your hand if you want to be a software engineer. Okay. Well, be a data scientist. Okay. As for why, there are many reasons. One is job growth. So 30% projected job growth over the next decade, according to the US Census Bureau. So, that's something. We're topping the LinkedIn job report of the last 3 years. That's something else as well. And it's not really going to go anywhere. So data is being collected. People are going to want data scientists. So you should be a data scientist because you should want to be wanted. Something. So yeah, it's definitely a growing industry, and I think it's going to be pretty resilient moving forward into the future. This is like the official page. And as for like use cases, there's something for everyone, right? Like every field, every industry, every domain, from like agriculture to, technology, obviously, to like airplanes, to home ownership, everything, people are gathering data everywhere, right? So data scientists can move into any domain. Yeah, and look, oh wait, Google's not on here, but Google also uses data science. So that's Google, Google search and ads and Google everything. All right. So these are just some more stuff. You can go anywhere with data science. The real, I think, pitch I would have for data science over most other career options is it gives you like lateral mobility, right? You can pick data science or data skills plus literally anything, like something you're passionate about. I don't know, like what's your favorite subject that's not computer science? Damn, okay. Like that's not that. Like what's anyone's favorite thing? Space. Boom. Space data science is a thing. There's a Viasat, this company, they had a data science intern position for like satellite. It was crazy. They were providing like internet coverage using satellites, and they wanted to predict when, people would not get internet. Like they were hiring data scientists. So space plus data science, totally a viable career path. Yeah, and you also get paid, which is cool. Yeah. And then these are just some of my hot takes. So this is all like official up until now, and then this is just what I think. Yeah, I think that maybe 30 years from now, like the business analyst will need to have some amount of data science like skill or literacy, right? So even if they aren't, jamming out in Jupyter notebooks every day, they maybe should know about like basic statistical principles or testing and training and how to validate data and so on. And the reason for this is because data is proliferating, right? There's like so much of it. Your Alexa is probably recording every single thing you're saying. Your houses are becoming smart homes, right? So all the sensors are collecting data, all of that. And that all has to be used by someone. Also, things are going to start getting automated away. Any problem with defined parameters or a problem that can be put in a box, a data scientist can do that, possibly, eventually, hopefully. Okay, so that's enough on my pitch. Become a data scientist. In order to become a data scientist, you have to go to TAMU Datathon. It's like a whole thing. Okay, cool. So now we're gonna get into the spicy stuff. And yeah, who here has familiarity with machine learning specifically, or yeah. What is a definition for machine learning? Anyone? Any brave soul? A machine that learns. Let me get some snaps for that. That's right on the money. George, what's machine learning?
I was gonna say machine learning.
That's what he just said, though. Yeah.
Great minds think alike.
I think you just copied what he was saying. Okay, all right.
The jury's out.
Right. So that's what I thought too, and I still think. Basically, machine learning is when computers learn patterns without telling them what to do using math. There is no consensus definition of like ML. I mean, there's like whatever that comes up on Google, but it's such a new and expanding field that it's not kind of set on one thing yet. So there's a broad array of statistical techniques like linear regression, if y'all have ever encountered that in your classes. That's machine learning. You know, that is machine learning. It's a ML algorithm, just like a gigantic neural net is also machine learning. It's training a model to do a thing. Cool. But more broadly, we can classify it into like 3 types. There's supervised learning, unsupervised learning, and reinforcement learning. And I'm going to go through all 3 of these just to give like a little basic rundown. But by the way, if at any time someone has a question, like please just stop me. What's a model? A model is a thing that takes an input and then gives you some output. So if, for example, I am a model because I took George's question and then returned an output, right? And typically a model does that in the context of machine learning, does that by taking in data and then mapping it to some kind of, giving you an answer. In fact, this slide may, give some, next slide may give some idea as to what that is. So here's just some terminology you may want about machine learning in general. So you have these things called features. So you'll hear people say features a lot in machine learning and it sounds intimidating. And I didn't know what a feature was until like this year. And I've been trying to do this stuff for like a hot minute. So features are the actual data that you're inputting into a model. So for example, in the past summer, I worked on predicting who would subscribe from like user activity, right? So the features in that user activity data set were like, what button did they click? When did they click it? How many times did they click it? Blah, blah, blah. These are all the features. The literal physical data, you're inputting it. Parameters are sort of the model coefficients or the weights that the model trains on those features. So if you think of a state-of-the-art machine learning model like y equals mx plus b, right? Then your parameter is m. Your feature is x. Your parameters are actually m and b, if that makes sense, because x is the independent variable. Cool. And then your response variable is y, which is the thing that is being predicted. So this is just so other people don't like, boondoggle you with, I'm a feature engineering specialist using this. It's just x. Okay. And then one more, small terminology thing y'all might want to know is training and testing data. This is kind of important. In fact, this is really important because our first datathon, when me, George, and others were in a team together, we didn't know anything about training and testing data. We just was like, it's just data. Just put in the model, it'll give you the answer. But when you have a data set, you're going to want to have some way to evaluate how well that model is performing, right? So let's say you have like a linear regression model and a big data set. What we did for Datathon is we just dumped all the data in the model into our linear regression and then called it a day. What you should do is split your data into training and testing sets. So you can dump your training data in the model to train it, right? So it will find your parameter values, like find a value for m, and then test it with your testing data. So this is just some semantics about training and testing data. It's a very general run through. There's a lot more nuance that's involved here, but not today. All right. So, all right, with that, let's go into the 3 forms of machine learning. So we can cover that, get this out of the way. There's supervised learning, which who here has heard of like supervised learning before? People say it, it's a word. So given your feature and your response variable, so x and y, find some function that maps x to y. That's the problem of supervised learning. So it's basically when the data is labeled. Like if I wanted to say, okay, is this, how much will it rain tomorrow? And I know, like, I don't know, the humidity today. Nah, I don't like that. How much will it rain tomorrow? And I know the temperature outside. So I'm trying to find some model that takes F of temperature and predicts, rainfall tomorrow. And I do that with data that, like historical data of, temperature versus rainfall. Does that make sense? So yeah, let's take this apple example. I like this one. You have labeled data that's like the image and then the name of, the apple or strawberry. And then you classify it. Is it an apple or a strawberry? Cool, labeled data. And there are two types of supervised learning. There's regression and classification. So in regression, you're predicting a continuous value. So for example, what is the temperature going to be tomorrow? Like 84 degrees. And then for classification, it would be, is it hot or cold? So you're, grouping observations into classes versus predicting the exact value. Yeah, that's supervised learning. It's like, has many, many applications, as y'all can imagine, like predicting anything from like the stock market to, am I going to graduate? Like that's a classification problem. That's like of a lot of interest to me. These are all types of supervised learning. So next type of machine learning task is unsupervised learning. And this is like a little more complicated, not complicated, but a little less intuitive, I think, to us than a supervised learning. So it can broadly be split into two types of problems, which are clustering and dimension reduction. So for dimension reduction, I'm not going to talk about it too much, but essentially, when you have many, many features, right? So let's say you're collecting data on someone's height, weight, their, like blood sugar, blood pressure, all of these different factors. You can only really visualize, two of those? Because it's like, X1, X2, and then X3, it's like 3D, and then 10D or whatever. So a lot of times to kind of collapse data down into dimensions, you will need special techniques to do that while still retaining the information that's, within the original data set. So this is, an example. They take cubes and flatten them into squares. That's cool. And then in addition, there's also clustering, which is where you take unlabeled data, whereas in supervised learning it was labeled, right? You know that the apple is an apple. Well, what if you don't know that the apple is an apple and you don't know that the strawberry is a strawberry or the watermelon's a watermelon? Then it will cluster this based off of similarity or dissimilarity between the objects. So one application for clustering algorithms is like, here's a map of population, distribution over like the city of Houston, right? Now, where should I put my department store, my 3 department stores in Houston? Then you would want a clustering algorithm to chew on that, come up with like 3 clusters and do that. So yeah, that's unsupervised learning. Finally, there's the fun one that's mysterious, which is reinforcement learning. Essentially, you have an agent in an environment. So this agent is like an actor, like a bot, or it's mostly always a bot. And you pass in either rewards or punishments, actually, based off of how they navigate their environment. So if they're making the correct decisions, you'll give them rewards. Otherwise, they don't do that. It's used a lot in self-driving cars, right? Like, if the car crashes, that's bad. But then if it indicates, that's good. So give it a reward. Have you all heard of AlphaGo or AlphaZero? Anyone? Yeah, that was a cool example of reinforcement learning and an agent that performed well. They trained some bots. Google trained, yes, Google. And DeepMind, which is owned by Google. Yeah, that's, yes, AlphaGo and AlphaZero basically beat the best. Well, AlphaGo beat the best Go players in the world, which up until that point wasn't really a solved game by computers. And AlphaZero beat the best chess engine in the world, Stockfish, which was thought to be like unbeatable. It was crazy. So yeah, that's reinforcement learning. And I know that this is all like really thrilling and amazing and fascinating, but none of this matters. None of this matters if you can't make these results meaningful, right? Like if you want to do data science or machine learning, or honestly anything, you have to be able to answer the so what problem. And with all of machine learning and data science, there's this problem of model interpretability, which is at the end of the day, these supervised learning techniques and unsupervised learning, everything is just so mysterious and black box. Like if you ask me why a neural network made the decision that it did, and it has like a gazillion different parameters and weights that it's like multiplying things by, I couldn't tell you, So it's really important that despite model performance, which is, these models are performing extremely, extremely well, and they're, getting incredible results and really good at predicting things, we still don't always know why it made the decision it did or chose the thing it chose. So this is something to kind of keep in mind, as your budding machine learning and data science careers begin. Always tie it back to a why. Over the summer, when I was working at Flickr, there was I had a model that was predicting whether people subscribed or not very well. It was really good. And I was like, wow, I really wish I knew how this worked, but I don't, because it's really hard to interpret. And there was another model that was much more interpretable and gave better results with regard to that, and was almost as good. And that ended up being a more useful model, right? Because you can actually know why it's doing the things it's doing. So yeah, make sure there's a so what at the end of, go for it.
Why exactly so you find the second model more useful?
So that's a great question. So a lot of times people aren't just going to ask you, okay, build out a model that does something well, build out a model that is always right. They want to know why the model is right? So my project over the summer was to build a model that predicts, whether users in the free trial period for Flickr will subscribe. But they don't just want to know if they will. They want to know why are people subscribing, right? Because there's a product team at Flickr that wants to know what people are clicking on when they are more likely to subscribe, which is why feature importance and knowing why things are happening is a big deal, right? Does that kind of make sense? Cool. All right. So yeah, I think that's most of what I have for you. If you want me to